All right, I want to thank everyone for joining us this afternoon or this morning or whatever time may be where you are. My name is Andrew Sartorelli. I'm one of the technical support specialists here at Autodesk for Autodesk Nastran In-CAD. I work out of our Munich office, and I've got a lovely picture here of myself in front of the Bundestag in Berlin. So today, what I'll be doing is talking a bit about troubleshooting, nonlinear analyses. Seems to be one of the most common topics from my perspective on technical support that we receive questions on. So hopefully I'll be able to give you a few pointers here about how to approach some of these problems. All right, so just some basics about the webinar series. So we do these on a monthly basis. Picking topics that hopefully people find interesting from our survey responses. Usually they're either hosted by somebody from technical support like myself, or we'll pull in somebody from the technical sales team to give a presentation as well. 20 to 40 minutes going over different topics. And we always have a Q&A session at the end. And as always, if you have any questions during the presentation, please don't hesitate to ask those, and we'll try to answer those live. Hopefully you guys have all already signed up for these, but if not, if you're watching this on YouTube, we do post these events on the Sim Hub, as well as on the forums. On each product forum, we've got a link there, and the video does get posted on our YouTube page a couple days afterwards. And just what's in the news for Nastran In-CAD. So for those of you using Nastran In-CAD with Inventor, there was the Inventor 2016 R2 release, and then shortly thereafter the R3 release. So with those updates, we have a shape generator within Inventor now, so you can see that to the right, a really cool tool there that's powered by Autodesk Nastran. And what that allows you to do is come up with some cool geometry to kind of add a little bit of simulation to the front end of your design. You've got Autodesk Force Effect, which allows you to do some free body diagrams within Inventor, and then the ability to publish in IFC format. A little bit older news, we did launch the Autodesk Nastran In-CAD 2017 beta in December. So there's still, I believe, a chance to sign up for that. If you're interested, you can go to beta.autodesk.com. And then in the really old news, we did launch the Autodesk Nastran In-CAD 2016 Subscription Advantage Pack in October. So that's an update available only to our subscription customers, which hopefully should be everyone. And that's available through your Autodesk account. If you look under Product Enhancements, you should see it there. Definitely a great update to add there. We added some really interesting mid-surfacing capabilities, as well as a bunch of other features and product enhancements that were customer-driven. All right, so now to the main topic here, troubleshooting nonlinear analyses in Nastran In-CAD. As I said, this is probably one of the most common topics I get questions about. So everyone's using it. It's the advantage to using a Nastran In-CAD over Inventor Stress is you get that nonlinear capability. So we'll be going over a few different topics here. So we'll start off with some model settings, what you can do in the setup of your geometry, your contact pairs to help your model. Then we'll be going over some parameters. So if you've ever taken a look at the Nastran parameters, you know there's probably about 500 of them that you can change. So I'm going to give you a handful today that will hopefully give you some good use when working with nonlinear models. I'll go over a few different error messages, just different things that you may encounter when working with a nonlinear model. And then I've got a easy demo, or what seems like an easy demo, but there's a few tricks here that we can use to get the model to run. So the first one, topic, setting up your model, is the nonlinear setup. So when you create a nonlinear static analysis or another type of nonlinear analysis, you're going to see this setup window appear in the model tree. And you've got a couple different options here. So the first, you'll see the number of increments. Typically that's auto-populated with 10. But one great trick you can do here is you can actually leave that blank. And what it does by leaving that blank is it allows it to auto increment. So it's going to start off at a very, very small increment size, and it's going to actually incrementally increase that size. So you'll start off with an increment of 1, and then it may increase that to 7, and then it'll increase that to 15, and then you'll be going in increments of 30 at the end. So it allows you at the start of your nonlinear analysis to hopefully initialize some contact and things like that, and then ramp up the analysis over the course there. The other one is if you're doing a nonlinear analysis, I always recommend turn on the intermediate output. You want to see what's going on during the progression of your analysis. If something goes wrong, you get a bunch of information in the output file, but it's a lot easier to just take a look and see what's going on visually in the results, and that may give you a better idea of what's going on there. If you've got a part that's kind of flying off into infinity, it's great to know that because you've got the intermediate results. And then we've got the other option there is the arc length on that first page. Typically, you won't need to make any changes to this option. So we'll leave that there. And then we'll go into advanced settings. So I'm just going to talk about the convergence, divergence area here. So I've kind of highlighted that in red. And you've got 3 options here. So by default, they're all unchecked, and your analysis is going to try to converge on displacement, load, and work all together. Now we can check these individually, and it's only going to check for convergence with that specific value. So what you never want to do is just do displacement. We always want to have either 2 of these combined or all 3. So I've got load displacement, load work, work displacement, load work and displacement. You want to have some combination of at least 2 or more. Technically, work is energy, so it's a combination of displacement and load. So you can play with the settings there, and we'll talk about one of the models here. Hopefully, an instance where you may encounter where you don't get a convergence on load, but you are getting convergence on work and displacement. We can actually change that setting there and it still get valid results. So next up, if you're doing a nonlinear analysis, you're probably working with some form of contact. So on the first page here, when you go in, you manually set up a contact pair, you got a couple different options. You've got a penetration type. So you've got symmetric versus unsymmetric, and then we've got an activation distance. So I'll just talk briefly here about symmetric versus unsymmetric. So we've got the green defined as what would be a slave, and the blue part's the master. So what we're looking for is we're looking for the slave to penetrate the master, and when we set this up, we can set it up incorrectly if we do master or slave. So if I go back a slide, we can see that we have the option to define either a master entity or a slave entity. Now it matters which one you're setting up when you do a master or when you do an unsymmetric contact, but if you switch that contact type to symmetric, it's not actually going to matter. So it's a little bit easier for those new to setting up simulations if you go with that symmetric contact type. And by default, it's going to go with an unsymmetric contact type when you set up contact initially. So it's an important change to make if you're getting some funky results with your contacts. And then you can see here we've changed that, and now we don't have that penetration occurring. So if you're getting some kind of penetration, the first thing to check is to see how your contact pairs are set up, and if you're using symmetric or unsymmetric contacts. So next up is the maximum activation distance. A lot of people ask, what is this activation distance? So I got a nice little visualization here. So say we've got this flat plate, and on top of it we've got a single element. kind of the golden orange color on top there is that single element with 4 nodes at the corners. You can see those nodes in red there. We're going to specify a max activation distance. What it does is it draws a sphere from those nodes, and that's the distance that we can interact with other parts for contact. And we can see that drawn now on the flat plate here. So if this golden element was kind of sliding on the flat plate, this would be the region enclosed by the black that we would be able to have contact defined for. Now this is important, especially when you have large motion in a model. You want to make sure that you've appropriately set up your activation distance to encompass the entire regime that you're expecting the part to move. If you don't set up enough, what you'll actually see is the part will just kind of fall off because you no longer have a contact between the 2 components occurring. And then advanced options. So generally, you're probably not going to need to go into advanced options. There's things there relating to stiction and things like that. So it's not something you're really going to need starting out. Next up, we've got the Nastran parameters. So those are found on the model tree down at the very bottom. You right-click and you can edit, and it's going to pull up the parameters there. So it's kind of hidden away there if you haven't seen this before. Like I said, it's all the way down the bottom, and then you pull up and you'll see we've got a bunch of different options here for directives, and then nonlinear solution parameters, solution processor parameters, things like that. So I'm going to go over a couple of these settings that can really help with a nonlinear analysis. Again, the basics of these parameters. You can find information on every single parameter in the Nastran reference manual. So you can actually click on the individual parameters. If I just go back, if I go back here, if you look at it says file spec, you can actually click on that, and that'll pull up the Nastran reference manual. And it's going to give you a big description there of what this does, what type of input it's looking for, what the default value is. One thing that's really important to be aware of is the type. So when it says real, it means like a double or a float if you're familiar with programming. So when you say 1, it's 1.0, and then if it's an integer, it's 1. So you can see here the S-line max act dist. If I look to the right there, I can see that the type is real, and what I've done is I've actually entered an integer there, so the box is going to be highlighted in red, and you won't be able to click OK to close out of the parameters. So it's just one thing to be aware of is that if you find yourself you've made a change to one of these parameters and you can't get back out of it, make sure that you've got the type correctly entered there. So the first parameter I'm going to talk about is found under Solution Processor Parameters, and this is linear contact. So this is great for troubleshooting if you've got a linear static model that you're going to try to convert to a nonlinear static model, and you want to make sure your contact's set up correctly. So if it's the default value is on, and you've got, say, separation contact defined, it's going to behave like there's separation contact there. But if you change that parameter to off now, it's actually going to behave as everything were bonded, or in Nastran solver terms, welded. So if you read the reference manual, it says welded. That's the same as the Nastran In-CAD bonded contact. So this is great to make sure that you've actually got the contact occurring between the components within your analysis. Next up, we're going into nonlinear solution parameters. So this is S-line slide type. So the default value for this is going to be dynamic. And what this is more of a proximity-based stiffness. It's meant for fast contact. So if you've got a part, sliding across and it's moving several elements in an increment. That would be what I would call a fast contact. And you can use it, it's ideally meant for things like slide fits. I'm going to talk next about static, which should not be used with slide fits. And this is a displacement-based stiffness, and it's meant for slow contact. So you're moving 1 to 2 elements over the course of an increment. What you don't want to have here is, like I said, a fast contact where you're skipping ahead on multiple elements, and then the contact is going to miss that movement. So you want to make sure it's a slow contact there, quote unquote. And it's really ideal if you're working with plasticity. So if you've got some nonlinear material properties in there, you want to be using this static type. So if you run into some trouble maybe with getting some spotty stresses in your contact results, I definitely recommend trying to switch over from a dynamic S-line slide type to a static. The next one is contact stab. So this is a contact stabilization parameter. And what this does is it generates stabilizing grounded springs on the contact surfaces in the model. So on each contact surface that you have defined in the model, it's going to go in and it's going to add some very weak springs, depending on the value that you specify, to hold those surfaces kind of in place. So this is great if you're getting some instability in the model. Right off the bat, it's not converging. What you can try to do is use this contact stabilization to hold things together until the contact really comes into play. So the stiffness should ramp down over the course of the subsequent iterations. This is done on the solver side. So by the end of the simulation, the stiffness should be very, very low, which will have a marginal effect on the overall results of the analysis. One of the other parameters we can set here is LG-DISP, so large displacement. So we can try disabling this and setting the value to 0, and not accounting for any of the large displacements, differential stiffness, or follower forces in the analysis, and see if we get some better results there that'll help us troubleshoot the model a little bit more. Next up, we have NLK Diag, again a nonlinear solution parameter, and like contact stab, what this does is it adds some very small stiffness to the model, except instead of doing this on just the contact surfaces like contact stab, this is going to do this across the entire model. So you're adding a very weak stiffness to the entire model. Recommended starting value is very, very small, 1e to -6. And this is, again, like the contact stab, it's going to slowly decrease this over the course of the analysis. So hopefully by the end of the simulation, it gets to the NLK Diag min factor. So it gets to a very, very small value, and it has a marginal effect on the results there. All right, so the next one, again, in nonlinear solution parameters. You're seeing you're trying to hear a lot of these, again, all found in that nonlinear solution parameters, because we're looking at nonlinear problems today. So we've got S-line stab KS facts, and what this does, it's a little bit different than contact stab and NLK Diag facts, where those added grounded springs. What this is doing is actually adding kind of a relative stiffness between the contact surfaces. So again, it allows for some form of stabilization in your model. If you're getting some instability, you're not able to get convergence very early on in the analysis. Again, you want to use very, very small values at the start. And what this actually does is over the course of the analysis, for each increment, it cuts that stiffness value in half. So hopefully by the end of the simulation, that stiffness has been reduced, significantly. So if you've got, 10 increments here, it's going to be reduced by 2 to the 10th power over the course of the analysis. The important thing to do when you're using this parameter is you want to check for strain, stabilization strain energy on your final increment. And I've got an example here where I'll show some of the output of an analysis run with that, and we can take a look at how that changes over time. What you're going to probably look for is ideally you want a value of less than 1%. Ideally, 0.1% or even less, because that's influencing the results there if you've got a large value, but it's stabilizing your model. So it's kind of a trade-off. And now just some common error messages with a nonlinear analysis. You've got the E5004, and its stiffness matrix is singular and non-positive definite. What this means is you've got some kind of 0 on the diagonal of your stiffness matrix, but what you end up with is just an infinite displacement. So something is floating off into space, going very far away from your model. So that, what does this mean? You don't have constraints properly set up in your model. Maybe you didn't add for all the degrees of freedom there. You've got improperly defined contact. So maybe you're expecting contact to hold some of the parts together, as it will be the example in my model, but it's not actually doing so. Or you've got singular elements. We'll talk a little bit about the first couple, but this final one is something you'd be more likely to see if you're using our other product, Autodesk Nastran, with maybe a different meshing utility than Nastran In-CAD. Next one is fatal error T2135. So I've seen this quite a few times when people are setting up nonlinear models. What they've done is, they've used some of the mid-surfacing tools within Nastran In-CAD, but the automated contact pairs that we can generate when using Nastran In-CAD in Inventor doesn't account for that change in geometry. So it's important to go in and manually modify those contact pairs so that they're edge to surface now instead of surface to surface, because the surface, most likely that was mid-surface, or maybe if you're thinking of a box, now we've just got a flat plate. We're missing 4 of those surfaces now because the part has been idealized as a mid-surface. And finally, you're going to get E5078, E5077, E5049. So you'll see a lot of these warnings and error messages. You've got your model and it's iterating, it's bisecting, but it's never really converging on a solution. And this just means your model, it's not stable, it's not properly tied down, there's something going on there. Eventually it's going to get to the max number of iterations and bisections, and it's going to throw a fatal error saying max number of bisections reached, and then the model's going to fail. Alright, so let's jump into Nastran In-CAD here. Okay, so what I've got is just a very simple assembly here. It's 2 parts. We've got a bolt part going into a block with a hole in it. What I've done is I've used symmetry in Inventor to cut down the model size. But what we'll see here is there's just a very, very small gap between these components, and if I use my tools and distance, let's see, we can see, here we go, 0.01 inches. So there's a very, very tiny gap between those parts. We want to account for that gap in the analysis. So I've got this set up as just a linear static analysis here. I've got a surface contact. I've left everything pretty much as default here, and we can run this. It should run pretty quickly. So we got a singularity when running this. Okay. So what I've got here is I got some of my settings left over from earlier on. So it's an important note there is that the parameters are the parameters for the entire model file and not just individual analyses. So you can see I've got multiple analyses here in my model tree. So those parameters carry through for all of those. So I'll just hit reset, and that should reset everything to default there. Again, if you have any questions, you can use the question box on the right-hand side, and we'll do our best to answer those live. All right, so now we can see the model's running, it's converging. We got some contact convergence there, so it's probably going to take a minute or so here for this to run, but we'll just get an idea of what the linear solution looks like, and then we can talk about the nonlinear solution. Because we'll see that the linear solution works perfectly fine, but now once I change that over to a nonlinear solution, it doesn't work. So why is it not working? All right, so it completes, and you can see we get some stresses. So it's being pulled up, and we can see stresses then occurring down on the bottom there. All right, so let's jump into the nonlinear. So again, I've just copied, if I were just to go set this as my active, just to do duplicate and edit, and then nonlinear static. This is all I did for the second one. Remesh the model, and that's it. I left it as is. So let's take a look. All right, so the first thing we talked about was the nonlinear setup. So let's go and take a look at that. So defaults, number of increments is 10. We've got intermediate output off. We look at our surface contact here. It's an unsymmetric surface contact. We do have the max activation distance set. So an important thing to note about that, when doing small displacements, the max activation distance as auto should be okay. But when you go into those larger displacements, that's when you want to go in and manually set that. And physical properties, we're just going to work with a standard isotropic material here. Okay. And now I'm going to run this. Alright, so this will take a minute here or so to get to the point we're interested in. But what we're going to see is it's just going to keep incrementing, or it's going to keep iterating, but it's never going to complete an iteration. We'll actually see some important data in the output file here that tells us something's going wrong, so it's a good thing to look at. Right. Okay, and we can see it actually goes in and sets up the contact stiffness and some transverse stiffness for the contact pairs that we have set up here. So I don't think I mentioned that, but we just have a surface contact or separation contact defined for this inner surface of the hole and then the outer surface of this bolt here. Okay, so we can see now it started out at 10% of load. So when I was talking about the increments earlier, it breaks down the load to a certain percentage. So using just the default, if you were to duplicate the analysis, it just goes to 10 increments. So 10% and 20%. And we'll show in the next one, when you leave that field blank, it starts at 1% and then slowly increases over the course of the analysis. We'll just give it another minute here. Perfect. All right. So what I'm looking for in this nonlinear analysis, I'm looking at the maximum incremental displacement magnitude, and I'll just pause this. So the maximum incremental displacement magnitude and the maximum total displacement magnitude. So these are, for me, really important fields when working with a nonlinear model that's not behaving correctly. I'm not getting the results I'm expecting. So I'll resume this, and we'll start to see some information stream through here. And we can see the work, load, and displacement convergence that I talked about earlier. See those values are very small now. But the important thing, the important reason to watch this total displacement magnitude is what you may see is it's very, very small, and then it jumps up to something very high. And this means the parts aren't, connected together. They're not interacting with one another, and the part is flying off into space. So your contact isn't holding things together as you would expect. So we'll let this increment a few more times, and then we should see the total displacement magnitude jump up very, very quickly, because this bolt here isn't actually is no longer interacting with the block. Just let it finish updating the matrix here, and then it should jump into a few more iterations. It does look like we have a question. All right. So from Eric here, is there a recommendation for what should be the slave and the master? And then can you summarize the difference between symmetric and unsymmetric penetration? All right. So what we're looking for with the master and slave relationship is essentially we're looking for the slave to try to penetrate the master surface. So if we have a master node penetrating a slave node, or part of the slave surface, then we're not going to realize that as contact. The nice thing is that only occurs with unsymmetric contact. So if you're not, an advanced user, maybe you're not too familiar with how to go about setting that up. What you can do is just go to a symmetric contact, and what that looks for is it looks for both the master the slave trying to penetrate the master, and the master trying to penetrate the slave. So to really, for most analyses, you can get away with that type of contact. There's some situations where you don't want the symmetric contact. If you got sliding, like if you have a buckle and a backpack that kind of snaps together. In that instance, you're probably going to want an unsymmetric contact, or if you've got maybe two cylinders, so you've got a pin within a hole, similar to the situation we have here, but the pin is actually rotating. Then it takes a little bit more thought about how to go in and set up that master and slave relationship, and what you might see is some warnings about your contact normal direction that would indicate you've got a problem with your master and slave setup. Hopefully that answers that, Eric. Let's see, from Lee. Would you be able to perform a similar analysis with a press fit part? So Lee, do you mean if you had a initial interference there? And while I wait for Lee, if you could just clarify that, I'm just going to pause this. And what we can see is now we look at our maximum incremental displacement magnitude. We see that that's shot up, so it's now 4,000. So a couple iterations ago, it was like 5e to the minus 5, and now it's jumped up to 4,000. So we know that something's going wrong here with our contact. Maybe things aren't interacting correctly. So that's like I said, that's a really good indicator. If you're watching your analysis, it's not converging, or you're not, it's stepping down the load level size. Take a look at this maximum incremental displacement, and it's going to give you a really good idea if there's something going wrong there. All right, so Lee said yes, you're looking for an initial interference there. I'm trying to think that the best way to do that now. We've got a couple different options here. We could do a penetration surface offset. Let's just take a look here. And what we can do is we can just quickly pull up the Nastran help. I haven't done a press fit before in Nastran In-CAD. I've done it a couple times in simulation mechanical. But let's just get an idea of what's available. So I'll go to manual. And again, this is the Nastran help. So whenever you're in a Nastran In-CAD window or dialog box, you can always press F1, and again, that just brings up the help page. So let's take a look here. All right, so that's not what we want there. I'm not sure if we have a way, Lee, of doing a press fit. If you let me get back to you, I'm sure we can come up with a couple ideas of best ways to do that. All right, and the next question here from Eric. Sometimes I see in a nonlinear analysis going well past the number of specified steps. So I'm not sure, Eric, if you mean the number of increments or the number of iterations. So there's a difference there. We could go back past the number of increments if we then start sub-incrementing because we're not converging. So say you've specified you're going to do 10 increments, but then it needs to cut your load down because it's not converging. It's reached the maximum number of iterations for that increment, and then it decides to kind of cut things in half. So you may end up with more increments there than you initially intended. All right, so I'm going to go now into this one here. Oh, so let me just stop this. We got to the point I wanted to show here again, the maximum incremental displacement magnitude. All right, and we'll go ahead and kill that. Zoom, and then kill. All right. So we'll set this as active. All right. So what I'm going to go in and do, I've changed this to symmetric contact there. I haven't changed the stiffness factor, the coefficient of friction. activation distance. Again, we're working with smaller displacements. We're not trying to pull this pin out, so we can leave the activation distance fairly small. And what was probably the likely reason for the model not converging in the previous analysis is, if you think about this model, it's not really stable. So we don't have a force kind of pushing this pin into the part that's holding it in. So with just a little bit of force, it's actually going to try to pop out. So that's probably what was happening there, and that's why we weren't getting a converged result. All right, so we're going to go in and we're going to go into our parameters here, and we'll go into nonlinear solution parameters. And the ones I want to use today, I'm going to go in and change, the S-line slide type, I'm going to change that to static. And we've got an S-line stab KS factor, and that would just go 1E minus 4. All right, so I did 1E minus 4, but we can see, again, this is, if we click on the field here, it wants a real value. So if we're going to go in, we just have to make sure we enter in that point. So 1 point E minus 4, and then we can run that. I think I still have my output file here. Let's just take a double check. Okay. So what we'll do is, give me just 1 second. I'm going to see if we can pull up the log file here so I don't have to let everyone sit through this again. Alright, so we will have to run this again. Hopefully it'll get to the point I wanted to bring up quickly here, is about the strain energy. So what we're going to see when using the stabilization now is there's a new output line in our Nastran output file, or .out file, that relates to strain energy for stabilization. It's really important to keep track of that when running, because we don't want that to be the overpowering force in our model. We want that to be very small. And again, the stiffness, due to the stiffness of the stabilization, is going to be cut in half for each increment, but it's still important to watch. So if we see, I ran one of these models earlier, and it had a strain energy of something like 65%. It's not a good value to have. You want it at least 1 or less. Again, it's, engineering guidance or engineering kind of wisdom there as to what values you should use, or what value is low enough for you to have not an influence on the model. So we'll give it a second to run. Again, if you have any questions, certainly feel free to post those right in the question window, and I'll try to answer all of those live here. So we'll give it it's going to take another minute or so to start assembling things, and then we'll start to see some important information stream through on the output file. So while that's going on, I'll just pull up the Nastran help. So with a lot of these warning messages, you'll see that they're now links. So I was talking about NLK or contact stab earlier. And what we can do is we can just search for that, and it just quickly pulls up all that information. And once you've opened the Nastran help, you've got the reference manual. So then, we're talking a lot about parameters today, different parameters that you can use. Again, nonlinear solution parameters, and you've got the whole list of them. So you can either click through, and then once you get through from one of them, from the model tree here, then you're back in here, and you can look through and look at a variety of them. So contact stab, S-line slide type. So we changed that again from dynamic, the default, to static, and it just gives you a description of what's going on there. So don't feel like you should just start toggling buttons, toggling these parameters. You've got a lot of information here about what each one means. If you ever have a question about should I be using this one or that one, certainly feel free to contact us in support. All right, so let's see where we are now. All right, so the first difference here that we can see, I deleted the number of increments, and we can see now that it starts at 1%. So instead of starting at 10%, we're starting at a very, very, much smaller, 10 times smaller. We're going down to 1%. And over the course of the analysis, that would just incrementally ramp up. I think it goes to, next it goes to 3 to 7 to 15 to 30 to 65, and then 100%. All right. It shouldn't take much more than a minute or two here to get to the first converge step. But you can already see, we've got, we're seeing 5% convergence in load. Compared to the first run, that was, we weren't really seeing any convergence. So we have a question here from Carl. Would adding friction in the contact settings also keep the pin from flying away? So it's a really good question, Lee. The reason initially it's not going to keep the pin from flying away is because the pin is not initially in contact with the hole. So that was one of the tricky things about this model. If we zoom in here, we can see there's just a very, very small gap there. Now, if we were running these and they were, perfectly, as a 4-inch diameter hole, and then the pin was 4 inches in diameter, and we had a decent friction value there, yeah, I think the friction would be able to hold it in place. But we've got that very, very small gap, and that's why we can't rely on friction to stabilize this model. All right, so again, we can look at the maximum number of incremental displacement magnitude, very, very small there. And then once we get a converge step here, we can see where we're starting to get convergence in displacement, load, and work. We'll see information about that strain, so we can actually see it here now. Percent, I'm just going to pause. Percent of contact strain energy due to stabilization. So right now that's 62%. And we want to get that down. Ideally, it should be around 1% or less is the kind of guideline that I've been using. So we'll resume. And again, versus the first model or the first run, we didn't get convergence on any steps here. Now we've got a converge step. I think we've just got our second converge step or increment, if I'm not mistaken, there. Now it's important to note here, if you're looking at this model and you see, oh my gosh, the part or the pin is flying through the hole, that's not the case. What's actually happening here is by default, we have it set to magnify displacements on output. If we look down here at the min-max, you can actually see that the maximum displacement value is 1.3 e to the minus 7. So we're really amplifying this displacement value to make it easy to see. But we can actually see, we're generating some stresses there. Right now, they're very small because the load is very small. But we should start to see those ramp up over the course of the analysis. So we also get some important information about contact surface penetration. So you may think, we don't want any. You may ask, why do we want penetration? There's always going to be some penetration in contact. If we just held it, absolutely zero penetration, 0.00000, absolutely, you're going to run into issues with convergence. It's going to be really hard to maintain that. So if you give it a little bit of flexibility there, very, very small amount of flexibility, it's going to prevent, convergence problems. So you never want to say, 0. You just want to give it a small value for allowable penetration. And in the scheme of things, 1 e to the minus 7 is pretty darn small given the scale of the model. So we can start to see some of the stress distribution is changing in the model here. And one of the things that I want to see over the course of this model changing is we're going to see part of the bottom surface stick, and then further along towards the main opening here, that surface is going to lift off. And again, we'll see the back of the top surface not in contact, and the front edge, the leading edge, in contact. So we've made it through another increment here. So it's gone up to 7%. So that's that auto incrementing. So it's really a great way. So you're not fiddling around with different increment sizes and things like that. Just let the solver choose it for you, and it's going to remove some of that headache. And again, we can see the strain energy due to stabilization is still pretty high. Hopefully by the end of the analysis that will start to decline there. It looks like we've only got about 10 minutes left here, so I'm not sure the analysis is going to finish. But I do want to make sure we open up in case folks have any more questions. And so while that is running, I'll just go back through. I think that was my last slide at the end there. But if you have any questions about any of the contact setting, any of the parameters I went through, feel free to ask those now. All right, in case anyone is interested, I think it's at the bottom of all the slides here. The slide deck is going to be available within the next day or two from this link down here. So it's autodesk.box.com/Nastran In-CAD IQ. So we should have folders on there. If you've missed any of our previous webinars, or you want any of the data sets or PowerPoints from any of the previous webinars, those are all available in that same box folder. You should see a variety there where you can quickly pull that information. All right, and let's just jump back. It's still solving here. So we'll leave it open for just another minute in case there are any more questions. All right, well, I want to thank everyone for attending today. I'm sorry we weren't able to see the very end of the model. Like I said, I will upload this data set to the box folder. If any of you want to take a look at it, you can feel free to download it, play around with it, as well as the PowerPoint. So hope everyone has a great day, and thanks a lot for attending.